Good evening. Tonight we are joined by Alan Hayward. I'm sure that most of you already know, but I'll introduce Alan anyway. Alan is a consultant at Cass Hayward Consulting Engineers. His career has been devoted to the construction and design of bridges. Alan will be discussing historic and recent railway bridge disasters, including some from personal experience. So tonight, Alan will present for around 50 minutes, 45, 50 minutes.
It's something like that, give or take.
Yeah, super. And then there'll be plenty of time for questions at the end. So if we could save those till after the talk, that'd be great. But please feel free to put them in the chat as we go along if you'd like to. I am going to mute all of the participants now and hand over to Alan. Thank you. Oh, sorry, Alan, I've muted you too. There you go.
Okay.
Brilliant.
Can everybody hear?
Yeah, we can all hear you. That's great.
Okay, good show. Well, good evening, everybody. Nice to see you wherever you are. I'm in Fleet in Hampshire, just for information. This talk, it's a mishmash of different bridges, really. They're either collapses or disasters or something gone wrong. Interesting question is, when is a disaster, and when it isn't? I suppose when there's a significant injury or loss of life, really, it becomes a disaster. I'm going to cover about 8 or 9 bridges, and 2 of them you may well have heard me in previous talks. The first one, the Dee Bridge at Chester, I gave a talk on a couple of years ago, and the Severn Bridge disaster a few years before that. And I'll briefly cover those, and along with some of these other ones. So we'll make a start. First thing is, this doesn't work. Ah, we're there. The second slide is really just showing, well, just so you know perhaps who I am, a bridge engineer. The bridge you see was a reconstruction of some 25 years ago, the River Exe, over the River Exe at Exeter and David Station. Similar in some ways to the Dee Bridge we're going to be talking about, in that it's got 3 spans, it's over a major river, and it's had a checkered history. Also, each track you can see on the photo there, each track has a separate structure, and that is common with the Dee Bridge as well. That was a very interesting structure, and you can see there that even in 97, yes, we'd got round to high-vis equipment, but we still wore collar and tie at that time. Not many people seem to now, which I find a pity. The Dee Bridge then we'll cover first of all. The Dee Bridge was designed by Robert Stevenson in the mid-1840s, and it carried 3 spans over the River Dee just outside Chester, 3 98-foot spans, and was unusual construction because it was this cast iron stroke wrought iron trussed girders, which was in vogue at the time. And there were about 60 bridges of this type around, going back to the 1840s. So it was quite a popular method of construction. But you can see here that on the left-hand side of the drawing there, that one span has partially collapsed, and there are remains of a train in the river, which was, of course, a disaster. 5 people were killed. So we'll go through actually what happened. This bridge was constructed as part of the Chester and Holyhead Railway under Robert Stevenson, and he was busy constructing it at the time, but he had finished the Dee Bridge some 6 months before the time of the collapse in May 1847. But another railway, the Shrewsbury and Chester Railway, was at a more advanced stage, and trains were already using the Dee Bridge under running powers, although the bridge had been built and was owned in effect by Robert Stevenson. So we have an interesting situation that the train which collapsed with the bridge belonged to the Shrewsbury and Chester, but the ownership of the bridge and construction of the bridge was by the Chester and Holly under Robert Stevenson. So you have an immediate contractual situation immediately. So what happened on this day in May 1847? A train left Chester. This is one of the, it was bound for Rewabun on the Chester and Holly, not the Chester and Holyhead, on the Shrewsbury route. And it departed 5 minutes late. So the driver was in a bit of a hurry. So by the time he got to the bridge, which was only a short distance away, really, 2 miles at maximum from Chester, he was doing about 30 miles per hour. That doesn't sound very fast, but at the time, that's a fair old speed, actually. So he reached the bridge at 30 miles an hour, and as the locomotive got to the third span, it got across 2 spans, all right. A collapse occurred. You can see the locomotive looks a pretty old-fashioned thing. You can see it's a very low-slung thing. This was a Stevenson patented long boiler locomotive. He made them with long boilers, so they were low down, giving you more power to create more power in the boiler. A large boiler, but a long boiler, low down, so that it didn't sway around too much, because these early locomotives suffered from swaying or yawing. So the train reached the third span, and the description I've given there is what that comes from the driver, his information at the inquest, the evidence he gave at the inquest. And as he got to the third span, he felt a sudden sink. The engine made a rear up, and we plucked it away. The tender sunk with the bridge, but we got it out. So the engine got across the bridge. The tender just about made it and landed on the abutment. And the 4 or 5 carriages, which are all very frail 4-wheel timber things, collapsed into the river. And the engine, in fact, the driver stopped the engine, realized that the stoker or the fireman had already fallen off and been killed instantly. But the driver drove on to the next junction, reversed onto the other track, and went back over the bridge on the other track, which was a brave and perhaps foolhardy thing to do, to set up the warning, stop all trains. So what was the bridge really composed of? Each track was a separate structure, having 2 cast iron girders, one each side, and spanning between. The deck construction was 9-inch square oak beams just resting on the edges of the flanges of the cast iron girders, and a timber floor on the top. There was nothing in the way of lateral bracing at all, so the lateral stability of this bridge was almost zero, actually. But the construction of the girders was the unusual thing. Cast iron, of course, that you were limited into the length that you could practically cast iron to about 40 feet. So faced with a span of approaching 100 feet, they would splice 3 lengths of girder together, reinforced with this bulbous part over the top, you see, and the thing was all bolted up. It was then reinforced to give extra strength, so they hoped, with these inclined wrought iron members, which were coupled at the third points to the bottom of the girders, and then angled up to engage with the ends of the girders, which had upstands at the ends. So you had a sort of catenary arrangement of these chains. So it was a compound truss, and the idea was you had the combined strength of the cast iron girder, which was of limited strength, strengthened, we hoped, by the wrought iron chains. And the theory that was used assumed that the strengths of the cast iron girder and of the chains could be merely added together algebraically, having equated the deflections. And the assumption for the wrought iron chains was that they were anchored at each end to an imaginary solid wall, if you like. In other words, a rigid arrangement, so that the it would act as a fully restrained catenary. That was the idea. So the sum at the bottom there is just working out the strength, assuming that the cast iron had an ultimate strength in tension of 6.5 tons per square inch, which was a fairly conservative measure of the ultimate strength of the cast iron in tension. So you added these two strengths together and then worked out your live loading and dead loading, and an apparent factor of safety against collapse of 4.3. In other words, more than 4. And Stevenson had expected a factor of safety at least 3. This whole thing was a misnomer, really. And the best way I can describe it is this rather silly way of imitating. A man gets into his very flexible bed, which seems to sag in the middle, with these bed heads which extend up at the ends, and he decides, I want to stiffen this bed up. So I'll get a strong piece of rope and I'll anchor it rigidly at the ends to the bed heads and anchored underneath the bed itself, and that will surely make it all a lot stronger. But he jumps into bed and it deflects the same amount. The ropes or the chains are of no use whatsoever, because what they are doing is pulling in the ends of the girder and giving an additional bending moment. In fact, the bending moment, if you work it all out, is exactly the same as if the rope or the chains were not there. I won't bore you with the mathematics, but if you go through the mathematics, you'll find that's what happens, that the ropes or the chains are in this system are of no use, simply because they are anchored to the thing you're trying to strengthen. So what caused the collapse of the bridge? Was it just due to this misnomer? Well, in fact, it was mainly due to that. So the main cause is the misconception, because if you just take the strength of the cast iron alone, you get a factor of safety not of 3 or 4, but of 1.3, which is dangerously low, of course. But there were other factors on this bridge. Straws which broke the camel's back, I called them. And the first one is that they put some ballast onto the deck on the very day of the collapse. And Stevenson had this ordered because he was afraid of fire hazard, because a bridge on the Great Western Railway under Brunel a few days before had caught fire and damaged cast iron beams underneath. So Stevenson got worried and thought, right, I'd better do something about this on the Dee Bridge, put some ballast down. But that ballast, of course, additional weight, reduced the factor of safety now down to 1.1. And then the other major fact is dynamic oscillations from lack of rigidity of the bridge. That was made worse by the behavior of this locomotive. And you can see there the locomotive. The natural frequency of the driving wheels and of the reciprocating cylinders was almost the same at 30 miles per hour as the natural frequency of the bridge, about between 2 and 3 hertz. And laterally, very difficult to work out the lateral natural frequency, but I had a go at it, around 2 hertz. So you had a structure which was very shaky vertically and shaky horizontally under this particular train at this speed. So that was really what was one of the straws that broke the camel's back. The other feature you'll see in the photo, the locomotive is shown with no outside cylinders driving the driving wheels because they're on the inside, but the actual locomotive had outside cylinders, and that makes a terrific difference to the yawing action that you get from reciprocating parts, and in fact doubles it. The lever arm you get of outside cylinders is literally double that of inside cylinders. So that caused an additional effect. I had to look very hard in all the evidence to find a statement by Henry Robertson, who was the engineer for the Shrewsbury line. Hidden in his text, it says the loco had outside cylinders. I almost picked that up by chance, and it never appears in all the evidence that it was a factor, but I believe it must have been. So what happened about all this? The bridge collapsed. What are we going to do about it? Bearing in mind there are 60 similar bridges built since 1839 by leading engineers. I mean, these are nobodies. Vignoles, Hawkshaw, Bidder and Gooch. All renowned engineers had all fallen into the same trap. So it's quite difficult to blame Stephenson alone. You know, he was the fall guy, really. So all the bridges had to be either propped or strengthened. You can see in the photo there some propping, timber props being used there to prop the third points of the span. And at least one bridge of that type remained like that for 60 years in that form. And of course, fully propped, it was okay. You cut the span to sort of 1/3 of the full span. But obviously these bridges were then banned. And there was a report, a government report, the commissioners reported the commissioners into the application of iron to railway structures, and that totally banned this type of construction, and said the compound truss system abandoned, higher factors of safety now up to 6 they wanted on cast iron, axle loading must be considered, which it never had been before, and dynamic effects must be allowed for, and wrought iron should be encouraged, not cast iron. So that's what came out of it. But just think about cast iron, it's excellent in compression. Of course, Stephenson's high-level bridge, 1850, still there carrying trains today, carrying road traffic and rail traffic. Wonderful structure, 5 spans, you can only see 2 of them there. Wonderful bridge. And Robert Stephenson admitted he didn't blame anyone else, he said, which I admit to have been a certain degree of oversight. He admitted it. He never blamed anybody, although the actual details of the design were actually done by his subordinates. He never blamed anybody for it. He took it on the hip, and that's a lesson in itself, I think. So we'll move on to another one, the Tay Bridge. Everyone's heard of the Tay Bridge, of course, the Tay Bridge disaster in 1879. 75 people died on a train. The crew and all the passengers died. It was a massive structure, and you can see there from the photo, across the Tay into Dundee. And in fact, had been opened 2 years before the collapse, and opened by Queen Victoria across the bridge, and Thomas Bouch, the designer, was knighted. So it was a fantastic achievement. And you can see there the arrow at the bottom there, that arrow is in fact where that was the first piece of the bridge to collapse. You can see that there are spans, 13 spans in the middle called the high girders. The trains ran through those girders to give you height for shipping clearance, whereas all the other spans are of deck type with the girders underneath. And the collapse occurred within these high girders, as they're called. And what happened, this was just after Christmas, 1879, and gale force winds, it really was howling gale, darkness, of course. And as a train entered the high girders, then a collapse occurred. And in fact, all 13 of the high girders were brought down as one. I believe that they'd all been previously weakened, which we'll go through in a minute. And you can see there that this is just before opening of the bridge. You'll see that the trains run through the girders, and it's a single track bridge. This is part of the problem. Very narrow bridges are, of course, more vulnerable than wide bridges. So it's only a single track. The diagram at the bottom, you can see the 13 spans, and the place where the collapse originated from was right there. So the superstructure, the girders, were all wrought iron, fine construction, but the columns were rather different. This is very sort of imaginative painting. It's a beautiful piece of work, but I don't think it's terribly accurate. But you can see there the that the piers are of cast iron columns and wrought iron bracings, very frail looking construction. And you can see the remains here of the piers. And the next morning, I mean, that's that obviously lost the train, lost the bridge. Just an interesting comparison, the height is 36 meters overall, not as high as Nelson's column, but it's getting on that way. And an interesting thing, the weight of one pier with the bridge on top is about 345 tons, whereas the weight of Nelson's column is 2,500 tons. And that's really part of the clue to the collapse as well. If you've got a lot of weight, you're less likely to turn over. A very light structure is extremely vulnerable. Well, the design of the bracings, which I've mentioned, that join the cast iron columns together, were a pretty dreadful bit of design, actually. They were each of flats about 5 inches by ½ inch thick, which were connected each end by a single bolt. And you can see here at the failure that the bolts are really just pulled out of the casting there. And that's one fault. The other fault is that all these bracings were tightened by a Gibbon cotter arrangement, which was a sort of folding wedge. But that's the sort of thing, I mean, who would think of doing that on a permanent bridge? It's a dreadful piece of work. To expect a bridge to remain rigid when you've just got these driven in wedges. And in fact, in the 2 years after the bridge opened, the maintenance people were going around banging these wedges in to keep the ties tautened. And they were experienced that the bridge was really shaking around when trains crossed it and in the wind. And the whole thing was just so shaky. To expect permanent bridge work to be reliant on just folding wedges banged in with a hammer. And of course, they loosen up under load and under wind loading. So that was a real omission. But the other major thing really was that the lack of design on the bracings was the wind loading, which Thomas Bouch had assumed. He had assumed £10 per square foot as wind loading. And where did he get that from? Well, he got it from the fact that he, at the time, was designing the Forth Bridge, which of course hadn't been constructed yet. And you can see his design was a suspension form of structure. And other engineers, other than him, William Barlow was one, they consulted the Astronomer Royal about what wind pressure should be assumed on the Forth Bridge. And he came out with £3 per square foot. Whereas, of course, the Tay Bridge is a series of very small, comparatively short spans, when, of course, the wind loading would be much more concentrated, such that you would expect perhaps £40 per square foot. So immediately, Bouch was under designing anything which was under wind loading, which would be the piers. And to an extent, I think he was misled. I think it has to be said. Although he was responsible, he was the designer, he took this £10 a square foot, and he was actually asked after the collapse, he did not consider it necessary to make any special provision for wind pressures on the Tay Bridge. So, I mean, this is the root of it, really. And of course, after the collapse, then his design for the Forth Bridge was abandoned. And of course, a totally different set of designers, Baker and Fowler, were brought in to produce a far more rigid structure suitable for wind loading. But you can see here how he was I think misled, but he was still responsible. This is just a diagram of what I assumed might have been the mode of failure. And it's not really the whole pier overturning, although there is some evidence of that by pulling out of holding down bolts on the windward side. But really, it's the bracings failing such that the piers just collapsed in on themselves. And when you look at photographs, there are a load of photographs of each pier with the remains after the collapse. It really shows that these piers just collapsed in on themselves because the bracings were totally ineffective or very shaky. And part of the evidence is that the spans of the bridge fell down 11.9 meters, I've shown there, from the base of the pier, whereas of course the total height of the bridge was much more than that. So it's evidence that the bridge fell in on itself. You can see here one of the photographs, there's a photographic collection in Dundee County Council. You can see here the pull out of holding down bolts. Notice those holding down bolts only went into two courses of masonry, which of course was totally inadequate for any significant wind loading. And of course the fourth bridge, which was as eventually built, was designed for a much higher pressure of 56 pounds per square foot, which is more or less the sort of pressure we might use today. And of course, the fourth bridge, a fine structure that's still standing, over-designed in some ways, but thank goodness it was. Well, they got the locomotive out. It was they found it inside the girders when they got them out, and that locomotive got rebuilt, and it survived, and it still carried trains up to 1919. But no driver would ever drive it across the Tay Bridge. Not surprising, is it? And of course, they rebuilt the Tay Bridge alongside for 2 tracks, which made it much more rigid. And you can see these massive structures forming the columns of the piers now. So we have a much more rigid structure, which of course is still there today. So that's Tay Bridge. I'll move on to the Lewisham rail disaster. We move on now into the next century, 1957, but a very tragic disaster because 90 people died. And it was caused by a train which ran through signals. The driver missed signals and collided with the back of a stationary train in front of him, right underneath this bridge, 2-span girder bridge carrying rail traffic above, and hit the column supporting 2 spans. And the 2 spans were simply supported and simply collapsed onto the train. And that's where all the deaths were really inside the carriages, which were underneath the bridge at the time. A really tragic disaster. Well, really, what caused it? This is going a bit beyond structural engineering, but this is the route coming out of London. It shows a straight track, really, but it's diagrammatic. It was quite a curvy track, as you see at the top there. Quite a lot of bends in it. But it was the cross section shows it's 4 tracks, and the train, which was a steam hauled train, left London in fog and darkness just around Christmas time, and the traffic had been very delayed by fog. The trains were all in the wrong order, so it was all a bit disorganized. The 4-track arrangement, you can see that the 2 inner tracks are close together and the outer ones are spaced apart. This was really because the station platforms intermediately were in these spaces called the 10-foot, whereas the space between the 2 middle tracks was the standard 6-foot. We call it the 6-foot. The engine was a left-hand drive engine, fairly modern construction, 1940s to 1950s. which was left-hand drive. Most of the old engines pre-war were right-hand driven. So we had an immediate disadvantage that the driver was on the left. The signals couldn't be put in the space between the two middle tracks. They were on the right-hand side. So the driver was on the wrong side, if you like, and he was reliant on the fireman who was on the right-hand side looking at the signals. Vision was restricted by the bends in the line and the fog. Conditions were pretty bad. And the driver missed a double yellow signal. He missed the next one, which was single yellow, which is a signal which means that the signal afterwards could be at red, as it was. He missed those first two. It's unclear why. They say he really should have shouted to his fireman, "What are the signals saying?" The fireman was apparently busy stoking the fire. So that's that. They reached the red signal and put the brakes on, but it was too late. And so they collided with the back of a electric multiple unit train, which had been stopped at signals in front of it because it was behind another train in front of that. Everything was very congested. So the steam train hit the back of the stationary train, and that's right underneath the railway bridge going over the top. See here, that's the top view, just shows the locomotive, which they rescued afterwards. It went back into traffic. You can see there's the flyover, the route carried by the train which was collapsed, impacted the bridge, is where that blue arrow is. So on a curve, curves are always bad news. Things always happen on curves. The train hit the back of the train in front of it, and the tender of the locomotive flipped sideways, hit that column. Taking that column out, of course, you had an immediate collapse situation. A feature of the locomotive was, with this streamline type, bullied Pacifics they called them, this particular one was built with a cab which is narrower. It was only 8'6" wide instead of 9 foot, because it had been built for a route with restricted clearances in tunnels to suit, because of very restricted clearances in a tunnel, which meant that the forward visibility, you can see there, the driver's got to look through that very narrow screen, whereas the normal most of the locomotives had a wider cab, 9 foot wide, gave you that additional vision. That's one of the factors. I mean, it's not the only factor. The driver should have been paying attention, but it's a factor that he missed the signals. There's the bridge you can see and the point of impact there. And you can see that the impact, the stationary train in front is there, and the steam train coming behind on the curve. You can see here the column which was collapsed was a steel column made of multiple UB or joist sections. The holding down bolts were not really adequate to take any huge forces. So my calculation is the force to topple the column could be between 50 and 100 tons. Quite difficult to work out depending on the anchorage of the bolts. Whereas the actual force, I predict, could have been much higher. If that bridge was built now, the rules are now that you always put columns at least 4.5 meters away from a railway track. That means you're much less likely to damage the column or hit the column indeed. So that was the situation. And the tender, you can see that very bad photo. That's the tender, which has flipped sideways, full of water, of course, weighing quite a 50 tons or so, flipped over and hit the column about there, with a force of around 50 tons. Today, you would have to design that column for 200 tons. So it might not save it, but it's a big help. So what happened as a result of that disaster? This is where the rule came. You must put columns at least 4.5 meters away, and you must anyway design for at least a 200-ton force. And also, additionally, it's much better if your spans are continuous, not simply supported. If you then take a column away on a continuous design, there's a chance that it may not collapse, whereas simply supported spans will. That's just a view showing the clearing up operation. It was very lucky in that a train was actually, at the time of the collapse, was coming along here. They stopped it just in time, and that would have made it even worse. Well, the bridge is still there. They put it back, such as it was, using a massive military trestling. This was stuff that was developed in World War II. Actually came from Colonel Everall, that came out of India. He developed this system of military trestling, which was used during wartime to repair bridges throughout Europe, in fact. In fact, some 50,000 tons of this stuff were made either in the UK and in the USA for restoring bridges after World War II. And this bridge, after 1957, they've used here to support this bridge. 1957, that bridge is still there, supported by the same military trestling. Pretty good stuff, actually, and you can still get it. It's now called Maybe HIMAT 75, and you can hire it. So it's pretty good stuff. So that's that one. So pretty dreadful. Now we move on to another one, the Severn Rail Bridge disaster. And I did give a talk about this probably back a few years now, of the Severn Rail Bridge. This bridge was built in 1879 to carry coal out of the Forest of Dean to be taken across into England. It never took off. Forest of Dean coal never really did anything. There were a lot of strikes, industrial action, and so on, and it never really worked. But the idea was to connect the Forest of Dean. There was quite a system of railways in there to get coal out. The bridge was then built to cross the River Severn and get out onto the main railway system. But what happened in thick fog, here we're back to thick fog again, at night, 2 petrol barges collided with one of the piers, that's Pier 17, just there, whereas the vessels which impacted the pier should have gone through one of the navigation spans, but though the vessels were lost in fog and drifted on the incoming tide of the River Severn. Now the bridge had 22 iron truss spans, cast iron columns, concrete filled, and 2 bigger spans on this side of the river where the deepest channel, shipping channel was, whereas none of these spans were here and here were suitable for shipping. You can see at low tide, the sand gets totally exposed. Well, the bridge, as I say, was built in 1879. It was a white elephant, really, and the traffic in that we move on to the 1950s was just this sort of 2-coach push and pull, which went across the bridge about 5 to 6 times a day, plus a few coal trains, but pretty surprised they kept it going for so long. And yet Pier 17, which was the one that got hit, you can see there. And you can immediately detect that the bracing in that pier is different from the other ones, and I shall come to that in a moment. Because in 1943, middle of the war, a vessel struck Pier 17, severely damaged it, and the bracings, which were cast iron, you can see there, were replaced by steel members, which obviously made it more rigid, more secure, and the bracings went full height, whereas a lot of the spans, the bracings were, you can see there were gaps. And some of the bracings, they had actually, going back to 1879, they put additional ones in because the Tay Bridge had just collapsed and they got scared. So that's why there's quite a lot of bracing, whereas the original design, a lot of these bracings were put in late after 1879. So you can see immediately here, it is strongly suspected that the 1943 damage probably weakened the bases of the columns. There's no evidence for that I know of, but apparently at the time a vessel hit this pier in 1943, bolts joining the superstructure onto the columns were fractured and sheared. So it was obviously a pretty significant event. Part of the problem was that the repairs in 1943 were done by the LMS, that's London Midland Scottish Railway, which had taken over the bridge from the Great Western Railway. So this change of ownership is, I think, a problem as well, because in later years, the ownership went back to the Western region of British Rail. I think that doesn't help. But in 1956, although the bridge was a white elephant, they decided to strengthen it because they were wanting to use it as a relief line to the Severn Tunnel, which had really taken most of its traffic away, needed repairs and maintenance on Sundays. So the idea was run trains across this bridge on a Sunday, which would be much heavier locomotives. So they were wanting to run the castle class locomotives, much heavier than the ones which were permitted to use the line, which were these much smaller ones. And so they did some testing here, quite elaborate testing from the research department from Derby, did a lot of work, theoretical work, and they were going to strengthen most of the diagonals on all the spans. And that work had started in the beginning of 1960. It started in April 60, and it had reached the fourth span by October 60 when things happened. What had been happening is since the 1950s, there was quite a traffic in oil and petrol by barge being taken up the River Severn from Avonmouth and other places, going northward and up the River Severn, and then as far as Sharpness, which is near where the bridge is, and onto the Sharpness Canal. The reason is that the River Severn is hazardous north of Lydney and Sharpness. So that's why they built the canal, because it's a much secure route, more secure route. These barges, which have been around since the 1950s, all up weight about 500 to 600 tons. So these two vessels are the two which you're concerned with. And the usual practice on these barges, they would only get into Sharpness docks on a high tide. You have to wait for high tide. And that's the only way you could get in the lock gates. So on high tide, they would come in, reverse, and then drift backwards with the incoming tide and get into the docks. That was the idea. That was the practice that had been going on. But on this particular night, of course, it was foggy and it was dark. These two vessels, the Arkandale and the Wasdale, one of them was an experienced skipper, the other one wasn't, very inexperienced. but they missed their place. They did the reversing and they got just to that spot where they collided with each other by accident and got locked together and were lost in the fog. And the tide of the Severn was still incoming. So they drifted towards the bridge, totally out of control, hit the bridge and demolished the pier. And immediately there was a fire created. That's my crude impression. Of course, there are no photographs of this. 5 people on the barges were killed by drowning or otherwise. But you can see there the vessels, all up weight of about 1,000 tons, hit the cast iron column, one of them, and it just collapsed in on itself, really, a bit like the Tay Bridge in a way. So the next morning, that's what they found. 2 spans gone, Pier 17 has disappeared, and the vessels still drifting in on the incoming tide, were found aground just there. And 50 years later, they're still there. Or just go back and say that the barges, of course, should have come into the docks, which is back to the left, and then gone up the canal and under a span of the bridge there, but they didn't make it. They drifted, hit the bridge there. I tried to do some calculations on forces. Impact force, I reckon, is about 170 tons, but the resistance was only about 50 tons. And the failure, I believe, we're talking about cast iron here, the columns were made in segments, of course, bolted together with internal flanged joints. And the bending caused by the pull of these bolts when they go into tension caused bending at that point there. And the evidence is, from bits of columns that were recovered, is that the failures didn't occur at the joints. They occurred a short distance away. So I think it's due to a local bending stress plus tension. Bit of an assumption that, but I think it's not far out. Also, you were hitting the column not square on, but so that the bracings were really being forced. The bolts connecting the bracings were only, well, they were 1-inch diameter bolts, whereas the thickness of the wall was only 1 inch. You should have a purchase of a bolt, of a threaded bolt of at least twice its diameter or something like that, not 1 times its diameter. So that connection was weak as well. Well, after that, there was a prevarication. British Railway wanted to restore the bridge, but Mr. Beeching came along, closing railway, so it really wasn't worthwhile. So the bridge was removed. 24 firms were invited for demolition. All but four of them declined. They said it's too risky going in that river. The River Severn is a very hazardous place. And eventually a firm called Nordman Construction, who had never done anything like this before, got the job for 75k. They brought in this German floating crane to start doing the demolition. But Nordman went into receivership. The German crane people never got paid any money, so they went home. So British Rail themselves had to take over the demolition, which was finally completed in 1970. That's 10 years after the collapse. So it's a real sad saga, really. I put this one on, Gould Swing Bridge, just for interest. Shows what happens when a vessel collides with a bridge. This is not quite like the one that in America the other few weeks ago, but this swing bridge didn't open in time, so this barge collided with the bridge, bent it a bit. We were involved with designing the replacement girders. We come on to one I've been involved with. This is not a disaster so much, it's a railway accident at Bexley, 1997. I got involved as an expert witness. It's quite interesting. And it involved with a train hauled by two of these locomotives, hauling these box wagons filled with spent ballast. And spent ballast, of course, if it gets wet, is very heavy. And the wagon which caused the derailment was overloaded. The total weight should have been 100, not more than 100 tons. It actually weighed 130 tons, which is part of the problem. And what happened? A train hauled by two of these Class 37 locomotives hauling these box wagons derailed on a bridge, and then these wagons really collapsed off the side of the bridge, causing quite a lot of damage. And 4 people working in arches underneath, brick arches under the bridge, were badly injured. You see there the arches which were badly damaged. So there were people working in these arches. But the bridge, which was the problem, is just back here, just out of the shot, really. The train was travelling in that direction, right to left. So the bridge which caused the problem, what was it? It was a very modest little bridge, only about 10 or 12 meters span, consisting of steel troughs with longitudinal timbers placed in them. And those timbers were just softwood timbers. And so there was no direct tie between the rails, except by the timbers contacting the sides of the metal troughs. And over some time, they had experienced what we call gauge spread. Because gauge spread is bad news. If you get enough gauge spread, the wheels drop between and you get a derailment. But they'd made attempts to tie together at the ends, which is the only place they could tie it together. Notice immediately that these longitudinal timbers, whereas normally you have cross sleepers to attract on ballast, but on these longitudinal timbers, the practice, which is not very good, is to cantilever on the end. But of course, that immediately brings in the phenomenon of seesawing. If you get a heavy axle right on the end there, it tends to tip up the timber, because these timbers are in short lengths normally, not full length of the bridge. So that's a potential problem. So cantilevered off the end is not good, because the ballast underneath is always badly packed, suffers from lack of maintenance, etc., under heavy wheels. So what happened at this derailment is that due to sideways forces from the train, pushed the timbers sideways against the side of the trough, and such that you got what's called gauge spread. You can see the condition of the timber is pretty terrible. The chair screws have worked sideways. The chairs themselves have moved sideways. So the whole thing's sort of collapsing over sideways. I was asked, what was the cause of the derailment? Well, there were 3 possible causes. One was gauge spread caused by these rotted timbers. They'd been there for years. The permanent weight ganger had been saying for months, these timbers are rotten, replace them. And nobody was doing anything about it. The replacement was deferred for months. So that was one cause of the possible cause. The second cause was overloading. The wagon was loaded to 121 tons instead of 102. So you might ask, how do we know if the wagon's derailed that it weighed 121 tons? Well, it was shown by the evidence that the wagon which caused the derailment didn't actually turn over, and they could weigh it, and they weighed it afterwards, and it was 121 tons. So that's a possible cause. And the third reason was that the train was doing 59 miles per hour in a 40 miles per hour limit. So is that a possible cause? The answer is, I think all those things are contributory. But the overspeeding isn't really, because the 40 mile an hour really was because of curvature on other parts of the line. So I don't think that's actually a cause. The overloading is a possible cause, because you can get sideways forces due to wagons at speed. So we did various things, made a model, And the immediate thing you see is that these longitudinal timbers are actually 3 bits of timber joined together. And they weren't joined together very well. There were a few long screws going through occasionally. And so you really had a classical pack of cards. And the timbers being so rotten, the chair screws worked sideways. The chairs themselves dug into the timber. So you had this lateral movement. And we worked out that the gauge spread to cause derailment could have been 80 mil, and you only need about 70 mil for the wheels to drop between the rails, which is what happened. All under the forces we call nosing. Nosing is a force you get in any train on track which is not perfect. The thing wanders from side to side, and the nosing allowance is normally 10 tons. It's arbitrary. It was derived in about 1943, and everyone still uses it, and it's in the Eurocodes as well. But it's a bit of an arbitrary force, but it's better than nothing. We also did a model railway, to represent the cantilevering of the timbers, causing the seesawing I've mentioned, which is a possible problem as well. Well, this business with longitudinal timbers doesn't go away. We're talking about last September 2024, a train carrying, again, a heavily loaded train, aggregate wagons, 9 wagons. The locomotive got there, the wagons didn't, and we had a derailment. No bridge collapse. And the main problem is that the chairs were chairs totally unsuitable for being on longitudinal timbers. Only 2 bolts. There should be at least 3, preferably 4. And these bolts are just sheared under lateral forces. The bridge is on a curve. Bridges on curves are always potential bad news. So the RAIB, the Rail Accident Investigation Branch, has sent out an urgent safety advice: derailment on bridges with longitudinal timbers. Well, that's scary. I can remember replacing bridges in the 1960s with longitudinal timbers. So it's about time they all disappeared. Next one I have is, just looking at time now, we're moving on, 7 o'clock. Docklands Light Railway. I designed this bridge across a road. It's very skewed on single column supports. So we used a torsionally rigid box girder construction. The IRA, one of the last bombs to be detonated by the IRA in Britain was then 1996. They detonated it almost under this bridge. Caused a lot of damage to the buildings either side. You can see the construction here, twin box girders on a single column. Needed to be torsionally rigid. The evidence was that the explosion, which had been literally under about there, had lifted the bridge off its bearings and bang back down again. And the bearings seem to have survived fine, but there was some damage, not too much. The webs of the box just on one side had been indented, distorted. So a lot of sums were done on the strength. Was the bridge okay still? And so we decided to put in these stiffeners shaped to the distortion. And we felt that was a better solution than try and straighten out the distortion, which could easily cause failures to the welds here. But obviously a full inspection was done to make sure there was no other damage, but the bridge has performed ever since. Moving on, the Stewarton Bridge collapse, 2009. This is a rail bridge just north of Carlisle, and collapsed under a train. Notice the bridge, the girders were, in fact, you can see at various points in the history, the middle girder, because there were 2 tracks here originally, the middle girder is actually totally buried. So how anyone could inspect it, I don't know. And the girder which collapsed, in fact, is the one over here. You can see what happens in railway scene. Over the years, tracks tend to get higher because every time you reballast the track, you put more ballast down and put the track back, it's higher. This tends to happen. And the cross section you can see here, got 3 girders. Originally there were 2 tracks, there was only 1 at the time of the problem. The problem was ballast was kept away from the side of the girder by timber planks there, and water just seeped down over the years and caused corrosion of the web. The bridge was, at the time of the collapse, had been assessed, but the assessor, who I will not name, had assumed that the webs were 1/2 inch thick. Well, they weren't. They were 1/4 inch thick to this outer girder and 3/8 thick under the centre girder. So there was an underestimate of strength. The bridge was about to be replaced because it was known to be in bad condition, but they didn't get there in time because under this train, with a class 66 having 21-ton axle loads, but the wagons, 25-ton axle loads, 100 tons. When you get 2 bogies directly over a span there, that's heavy loading. The wagons caught fire and the wagons went all over the place. The bridge is just on the right there. And there's the collapse. You can see the plane of failure there. And at the end, where the shear is highest, of course, the web has totally failed in shear. Shear failures are the enemy. Bending failures are rare, but shear failures happen suddenly. That's a real lesson. I think it's a lesson for codes of practice, really. Be very careful about shear. The echoes of this in the, this is not a bridge really, it's a signal box that failed in 1965 at Clapham Junction. And it failed at the end, in shear, the diagonal here, tension member failed. Why? Because you couldn't maintain it, because on the inside, you can see that the bridge on the inside, you've got all the timber work of the signal box. You couldn't do proper inspection. Inspection was very difficult. So this thing just corroded, and in the end, one morning, bang, it went. So the lesson is really, it's hidden parts. This is the last one. I'll skip through this quite quick. The Kerch crossing to Ukraine. In World War II, the Germans had constructed a ropeway across the Kerch Strait. And then they had started a road rail bridge, but that got destroyed because they were retreating from the Russians. Then the Russians came in and thought, well, we're going to have a bridge. So they built this bridge, marvelous structure, including swing spans at the middle, enormous structure. But it was destroyed by ice flow in 1945, so they took it down. Then Mr. Putin came along and he invaded Crimea and decided he would build a bridge from Crimea to Russia to replace the one that had been taken down in 1945. And it was combined road and rail. And you can see that the rail, of course, remains on the level and the road goes up and down with a navigation span there. 18 kilometres long, built in 4 years. I mean, a terrific achievement. But Ukrainians decided to do something about removing the bridge. This shot, you can see there, traffic moving along there. In the distance, there's a lorry. And next to it, there's another vehicle. It was a car, I think. That lorry obviously contained some pretty high explosives. because bang. I'm sorry, this sometimes turns into a movie. I don't think it's going to do it tonight. But that's the big flash of the explosion, and the vehicles you could see nearer to you are still there. 2 or 4 people were killed. And of course, we're talking about the road span, and there's the collapse which occurred and there. But the explosion was such that a train which happened to be travelling on the rail bridge adjacent with petrol wagons caught fire. Whether the Ukrainians intended that, it's never known, but that train was moving, and the lorry which caused the detonation was there. So did they plan all that? Nothing's ever been revealed. It's surprising if they haven't planned it. Remarkable bit of planning. And there's the road bridge which has collapsed. The rail bridge, of course, was still there, but that fire burnt for at least 2 or 4 hours, apparently, before they could put it out. And the collapse mechanism, this is my supposition, this is the road bridge now, because it was in sections of 4 spans, continuous 4 spans. So the explosion is there. So you get a total failure there and a deflection that pulls the ends in. So the ends drop off the bearings. So that's the sort of mode of collapse, I think. And the rail bridge went on burning, but still standing. So what happened? Well, the Russians came in and pulled the train off. They apparently very quickly uncoupled the front of the train and took the wagons away. But you can see what happens to fire on steel. The wheel of the wagon must have been just there. So there was obvious damage. So was the structure of the rail bridge damaged? There must have been some damage, but they apparently carried on using it restricted loading and restricted speed until sometime later. See, the rail bridge is still there. They replaced the road spans, the 4 spans, and Mr. Putin said, I want it back by July 23. When in fact, he got it back in 57 days, which is remarkable. Absolutely fantastic achievement. But the rail bridge, nothing, very hard to find out what happened. But what is known, they replaced the 1 span that had some damage by launching a new girders across in May 23. So they obviously were concerned about the rail bridge. I'll just quickly finish now, but what's hitting us now with climate change is flooding, foundation scour and instability. This goes back a few years, the Ness Railway Bridge, but undermining of the brick arch spans caused the collapse. No one died, but it was pretty severe, and that had to be replaced by a large span steel structure. And a recent one in the last couple of years, this Newnham Viaduct, River Thames, north of Didcot, the abutment at one end started sinking, and you can see here the abutment started sinking. It left the wing walls behind. You can see there. So they propped it up and put new piled foundations here. And this is all a contribution by flooding and increasing rain, really. There's nothing new about washouts undermining a scour of foundations. This goes back to 1961, and an ex-colleague of mine from British Railways was concerned with this. He designed the replacement, but it was caused by scour of foundations, but he did pile foundations and replace the bridge. It just shows there's nothing new about flooding, but it's just getting worse. Final slide is a famous engineer, and he is, to my mind, a very renowned engineer, William Fairbairn. He advised Robert Stephenson, and he said to Robert Stephenson on these trussed bridges like the Dee Bridge, don't do it. He said, I don't like it. And he was exactly right. And he then advised Robert Stevenson on the Menai Strait Bridge, which, as you all know, was originally designed to have chains helping to support the wrought iron girders. He said they're not necessary, and he was exactly right. William Fairbairn, a really famous engineer, trained as an apprentice millwright. I mean, he was a practical guy. But look what he went on to do. Bridges, locomotives, ships, cranes, mill buildings. He did everything. And his statement, I think, is worth repeating. In many of our operations, we are the children of habit. We tend to do what's been done before and hope for the best. It's not always right. Well, that's it. Thank you. I'm happy to answer any questions in a moment or two.
That's brilliant. Thank you, Alan. That was absolutely wonderful. Did you want to take a couple of minutes, or are you
Yeah,
happy
I'll be back in a couple of minutes.
Yeah. Okay, great. So whilst Alan just nips out, I just wanted to let you know that our next talk on the 3rd of March will be Coetzee Axisec on a multi-scale investigation into oxide jacking of 2 historic masonry structures. So Coetzee's case studies are Blenheim Palace and Salisbury Cathedral. Coetzee is a DPhil candidate at the Department of Engineering and Science at the University of Oxford. We've actually got 2 talks in March this year. Our second talk will be on the 31st of March, and that will be on the Crystal Palace subway project. The architect, Clive England of Thomas Ford, Ian Harper, Historic England Partnerships architect, and Christian Petrescu of the Morton Partnership will be given a combined talk on the Crystal Palace subway. Brilliant. Alan's back. Alan, I think given the time, we've probably only got time for 2 or 3 questions now. If we try and wrap up by 7:30, does that sound okay? You've got you on mute, Alan.
Okay.
Does anybody have any questions?
That's what I like, a good silence.
Yeah. James.
Yes, can you hear me? Is that okay?
Yes, we can hear you. Yeah, brilliant.
Well, it was really only a reflection, I suppose. First of all, I'm sure everyone's saying to themselves, "Yeah, that was great." So thank you very much indeed. Reflection on Lewisham. I tuned in and I thought, my goodness, this is topical. My dear late father, he got married that year. He was working in London, 1957, December. He got on the train at Charing Cross. He missed the one before, and he got on the train and set off. And he was very late home. He should have been on the one before, and he might have been killed. So Lewisham, which I've passed, the 15 years I worked in London, always passed up and down on the line from Sevenoaks. It is quite, it's quite remarkable because you look at it, and thank you very much for identifying the maybe HIMAT 75 system for me. You see what you know to be something that's temporary and has clearly been there for a very long time. The story goes that my uncle phoned my mother to say that there'd been a tragedy, and he was sure that my father wasn't on the train. And indeed he wasn't, but how he was sure, I'm not quite sure. But it was, a salutary lesson. And one of the things that comes out of your talk, I think, is a reflection of Baltimore, because yes, it's not a barge hitting an unprotected pier, but it is a train, and the protection of the support structures of our bridges is something that we still haven't got the measure of, is it? Question mark.
No, you're quite right. Well, that was very interesting, almost first-hand experience in Lewisham. But yes, I mean, protection of structures, something that's often neglected, and we have to have an accident to find out about it. But more could be done. You know, lateral forces in general is something we tend to neglect, and we don't know how to calculate them.
Mm.
And of course, they can be huge. I mean, Baltimore is, you're talking about thousands of tons of, what was the vessel? What was 100,000 tons, was it?
Yes, it was
Absolutely
I
huge.
can't
So
remember, but
the
it was
impact
certainly enough.
forces, nothing would stand up to that. You've just got to have protective measures to keep the steer them away, really. Get to a point where you can't design for such enormous loads.
No, thank you.
Does anybody have any more questions or thoughts? I think everybody's in stunned silence after that, Alan. That was excellent.
Well, okay.
Thank you again.
If anybody does have any real queries, or you can always get to me, email me if you got any particular points.
Fabulous. Okay. Well, we'll say good night then.
Okay.
Thanks very much.
Thanks for your attention, everybody.
Thanks very much, Alan.
Thank you.
Thank you. Thanks.
Okay.
Very good. Thank you.
Thanks a lot.